Well, hello, and yeah, this will be the final presentation for today, and we're going to look at some regulation and efficiency related to transformer performance. So we've produced this equivalent circuit, and within this equivalent circuit, we have some losses, and so what we're going to do is look at efficiency. So when we look at efficiency, we need to look at real power. So in this equivalent circuit, we're really going to be interested in copper losses and iron losses. Okay? And typically, the resistive load, load is normally purely resistive. So in other words, the power factors are going to equal 1. So the input power then is we can define as output power plus losses. Okay, we must always get less out than we put in, otherwise it's not a physical system. And we can define efficiency as output power over input power. So then if we just substitute this in, we can get this equation here. And if we rearrange this equation at the top, then we can also define efficiency as input power minus losses over input power. So what we want to calculate is the maximum power efficiency point of our transformer. Because when you measure the efficiency against output current, you get this kind of curve. And so there's a point of maximum efficiency. So we can calculate efficiency. So if we look at this previous formula, we can calculate the input power, and we can divide that by the input power plus the iron losses plus the copper losses. So we can rearrange this equation a bit by dividing by the input current to get this expression here, and we can say that the maximum efficiency point is when this denominator, when it's differentiated with respect to the input current, is equal to 0. So if we do this, then that's a constant, and we have an I1 term here, so that becomes minus I1 squared, and that becomes R1 equivalent. So we end up with this expression here, and from that we can conclude that the iron losses must equal the input current squared times the resistance related to the copper losses. So we can say that power iron is equal to power copper for maximum power efficiency. I hope that sort of follows through okay. Please, if you're not, so just go through that on your own time for a few minutes, just to make sure that you're okay with that. And here's an example you can try as homework. These PowerPoints will be on Moodle in a little while, in fact. So please go through this as homework. And the next slide will show you the solutions, but please go through the example first before you look at the solutions. Okay. So next we want to look at something called voltage regulation, and let's consider case 1 where we have an open circuit as a load impedance across the secondary load, and we can say this V1 then is going to equal Vp times the number of turns in the secondary divided by the number of turns in the primary. So in this particular case then, we can, if we had a black box transformer, we can calculate the turns ratio. by measuring the value of V1. And then we connect a load to the secondary, and what we can determine is that the secondary voltage must be less than Vp times Ns over Np. Why is that? Because we must draw a current and there must be some power loss. So the voltage drop across that resistor. So what that means is that we can draw this kind of graph where we have the maximum finite, where the voltage output across the secondary for an ideal transformer, and we have the voltage for full load, and it will drop in a linear fashion. So we can define something called voltage regulation, and that's the short circuit voltage, the open circuit voltage of the secondary minus Vs. So at any particular point of a load, we'll have a Vs, and we divide that by the open circuit voltage and multiply by 100%. So we can work out the voltage regulation at any point along this line. Now typically, the voltage regulation is better than 5%. We don't want this to drop too much from full load conditioned to the open circuit. So here's another example you can try as homework. And there's no solution slide for this, so I shall post the solution onto Moodle or something. I'll give you some time to do it, obviously. Or maybe we'll go through it actually in example classes. So next week will be the last lecture actually on transformers, and although there'll be 2 lectures, but it'll be the last week of transformers, and then we'll have some example classes all the way from single phase AC through to transformers. So just to sort of summarize all that, if we have an ideal transformer with no power losses due to copper or the iron, then we'll have an output voltage which is constant for output current. A practical transformer will see a drop in the output voltage because we're drawing current through a loss resistor. And similarly, if we were to draw input current over output current, then we would have some input current for no output current. Why is that? Because we saw we had hysteresis losses. So for 0 flux density, we add non-zero current, and that is input current. Okay, so this relates to hysteresis and also eddy current losses in the iron core. And for an ideal transformer, the efficiency will always be 100% because there's no losses. But for a practical transformer, we've seen that we get this kind of curve, and we have a maximum power efficiency point where the copper losses and the iron losses are equal. So basically, if you can understand how we get these 3 curves, then you're going to be fine. You understand transformers that are used in a power system. Okay, any questions, please ask as usual. I don't seem to get many questions, but I'd be very happy if I can't answer them, and there may be cases where I can't, then don't worry, I shall try and look the answer up or figure the answer out and respond by Moodle or the next lecture. So yeah, so please ask questions, or if you don't ask questions now, or you don't want to ask a question now, that's perfectly fine. I understand, but you can just then perhaps send me an email or send me a comment on the forum, or you can book an office appointment. Okay, if those times for the virtual office hours are not convenient, please let me know. Suggest other times, and I'll see if I can fit them in. Obviously, we have a problem with time difference. It doesn't make things easy, but I'm perfectly happy. Even maybe on a Saturday, I'd be perfectly happy for an hour or so to give some virtual office hours. We're in lockdown here, in virtual lockdown, well, not full lockdown, but sort of lockdown anyway. So it's not as if there's a lot to do at the weekend. So please, yeah, if those times, look at those times if you want to see me. If they're not convenient, then please just let me know and I'll put up some more appointments. Try and suggest, please, some convenient times. But yeah, please let me know if you have any problems with the example sheets, with the lectures, with some of these problems that I've suggested you do as homework, or any background reading that you do if you don't understand something. Please let me know. When you book an appointment, it will ask you to outline what you want to discuss. This gives me a chance to have a look. Otherwise, I'm going to spend we'll spend the whole time for those appointments me finding out what it is you're having a problem with, rather than solving your problem. So please give some explanation as to what your problem is. Okay. Yes, so thank you very much, and I think that's the end of this particular lecture. If you don't have any questions, I'll see you next week. Thank you for your attention.